How does the free body diagram of a car going through a turn at constant speed relate to its acceleration? And maybe another way I could put that is I could say, well, cars going through a turn, does it need force for that? And if so, what force? Right? Well, based on our learning of centripetal acceleration, we might be able to answer that. I've actually got some pictures here in the slide, so I'm just going to go ahead and show the answer for this. And it starts here with the view from behind of a car, and it's saying it's moving in a right turn. So what does that mean? That means, I think that means the acceleration is going to point rightward, but we're going to start with the FBD here and put in a system point, and we're going to have gravity. We're going to put in a normal / support force. All of those make sense to be there, right? I've put them in words because I actually developed these pictures for a conceptual physics class, so we use different notation than we tend to use in this class, but that's perfectly fine. It's, in that sense, in this class, I might say F sub G, F sub N, F sub maybe T for traction, or maybe F sub F for static friction, right? So there it is. There must be traction to keep the car in the turn. And then how does that relate to the acceleration? As I said before, it's to the right because the car is in circular motion. And in that sense, going back to the kind of question I raised verbally here, is like, which of these forces really keeps the car in the turn? And it's the traction force. And if you don't believe me, try doing this on some ice. You'll find out instead of going in a turn, the car will follow the tangent line to whatever curve it was in when it hits that ice and possibly collide with the side of the road or something else if that continues.